Hi, science friends. Today we're going to talk about sex-linked genes. So sex-linked genes are genes that are located on the sex chromosomes, okay? So remember, the sex chromosomes are the X chromosomes and the Y chromosomes. They're at the end of the karyotype. They're that 23rd pair called the sex chromosomes. So females are going to be XX. Males are going to be XY, okay? So this Y chromosome, if you look at it, it's much smaller, okay? We only see one gene shown on the Y chromosome, and it's the testes determining factor. Sometimes you'll hear it called the sex determining region on the Y, okay? Because that's what determines your sex. If you get a Y chromosome, you will develop testes. If you don't get a Y chromosome, you'll be a girl and you won't develop testes. And so that's really the only gene that is on that Y chromosome. Versus if you look at the X chromosome, it's much larger. And you see several genes up and down through here. Genes for things like hemophilia, that's when your blood doesn't clot and you bleed freely. Color blindness, an immunodeficiency disease, we're not going to talk about that one. X inactivation center, we will talk about that just a little bit more in a minute. Melanoma, which is a skin cancer, and then a condition called muscular dystrophy. So those are all things that are coded for on the X chromosome. They're genes that land on the X chromosome, okay? Now, one thing that's super important that you understand about sex-linked genes is that in men, because they only have one X chromosome, if they have the dominant allele on that X chromosome, then they will have the dominant version of the trait, okay? So men would be like this, right? They would be X big N, Y, and they would show the dominant version of the trait. If they were X little n, Y, then they would show the recessive version of the trait. In the past, in order to have the recessive version of the trait, we would say you had to have little n. But for men, because it's on a sex chromosome, they only have one copy of that allele. And so if they get the big copy, they're going to show the dominant version. If they get the little copy, then they would show the recessive version, okay? Versus in females, they could be X big N, or they could be X big N, X little n, and show the dominant trait. And then on the recessive end, a trait, they would have to get two copies of the recessive allele. So let's think about things like color blindness, okay? Color blindness is a recessive trait. So that means little n codes for color blindness, okay? So for a male to be colorblind, he only has to get one copy of that bad allele, versus females have to get two copies of that bad allele. And so for that reason, color blindness is a lot more likely in men than it is in women, okay? And the same is true for all of these genetic conditions. All of these are going to be more common in men than women because they only have to have one copy, whereas the women would have to have two in the recessive condition, okay? So let's look at this Punnett square. Now, anytime you're doing a sex-linked gene, you have to write your Punnett squares like this, okay? You can't just do big C, little c anymore. You have to show if it's male or if it's female. So a father with normal vision, he's going to have to be the X big C, Y, okay? If he would have been colorblind, he would have had the little c, X little c, Y. The female is a carrier. So a carrier means they're going to have one big letter and one little letter. They're going to be heterozygous. So she's got a big C and a little c. And so if we look at our Punnett squares, these two are going to have our XXs. So these are our females, okay? One of them is going to have normal color vision. She's got both big C's. And the other one is heterozygous, and so she's going to be that carrier for color blindness. Versus our males, One of them is going to have normal vision because he got the big X from his mom. The other one, however, got the the big C from his mom, not the big X. The other one got the little c from the mom. And so that son would be colorblind. So for our females, 100% of them would have normal vision. But for our males, 50% of them would have normal vision and 50% would be expected to be colorblind. Okay? So anytime you see a genetic outcome where the females and the males are broken down separately, we've never done that in the past. Any of our other Punnett squares, we just said, 100%, 25%, 50%, whatever. We didn't specify for males and females. But if you see it broken down with males or females, then that should lead you to say, this is a sex-linked gene, okay? The gene that controls this trait is on the X chromosome. It's a sex-linked trait, okay? And we'll do some more examples to practice this in your assignment for today, okay? Now, let's also talk about Barr bodies. One gene that I told you that was on here was the X inactivation center. And so females, if they get 2 copies of the X chromosome, one of them are going to be inactivated, and that's called a Barr body, okay? Females are going to be XX, males are going to be XY. And so you might think, well, females are going to have extra genes than the males are. Yes, they would, except one of these is going to be inactivated, and that's called a Barr body, an inactive version of an X chromosome. Now, last thing let's talk about today is non-disjunction. One other thing that can happen that causes abnormalities in chromosome number is non-disjunction. And so non-disjunction is when chromosomes fail to separate in meiosis, okay? So remember, in meiosis, we have 2 rounds. We have meiosis 1, where the homologous chromosomes divide. So these are our homologous chromosomes, and they're going to split apart. So see, one of the red ones went over here, and the other red one went over here. Now, what happened to these guys? Those 2 didn't split apart. Instead, both sets went over here, and there's no yellow over on this side like there should be. And so in the gametes, look, we should have 1 red and 1 yellow, but instead we have 1 red and 2 yellows. 2 yellows and 1 red. So these have extra chromosomes, 1 extra chromosome for each of those. These, however, have too few. They're missing a chromosome. And so this process, when they don't separate, is called non-disjunction. This leads to things like Down syndrome, okay? Down syndrome is sometimes called trisomy 21. Trisomy means that they have 3 copies of the 21st chromosome. And so their sperm, or the egg that they were fertilized with from their parent, had 1 extra copy of the 21st chromosome. And so that was caused by non-disjunction, and that results in conditions like Down syndrome or trisomy 21. Okay. Now, this can also happen in meiosis 1, where the homologous chromosomes fail to separate, but it can also happen, this doesn't really show it, but in meiosis 2, if the sister chromatids didn't separate correctly. So it can happen either of those places. Okay? So those are some genetic disorders as well. Now, tomorrow, whether we are virtual, I don't know anything, maybe we will be, maybe we'll hopefully be back in school, you all are going to start on a genetics disorders project. And some of you may choose Down syndrome as your genetic disorder that you're going to do. So we'll talk about several different genetic disorders that happen from things like non-disjunction or other things as well. Okay? So you all have a great day, and let me know if you have any questions. Make sure you do those sex-linked Punnett squares. Bye.